Welcome everyone. Today we're going to start our look at momentum, and we're doing an exploration of momentum, and I'm very excited. I love this section, okay? But now where do we start? Well, let's have a look. Have you ever thought about why it is so difficult to stop a rugby player when they are running? Now, if you've ever watched a little bit of rugby, you'll know especially the big guys, like the ones who are in the lock and the scrum, they're very difficult to stop. And then if you listen, the commentators will use words like the rugby players scored a try because their momentum took them over the line. Or in a scrum, they'll go, the momentum of the scrum got them over the line. And you know what? As a science teacher, this is the one time when I go, actually, they got the term right. They used the right words, because often I have to be careful when I watch movies, because I go, oh, the science is bad. But it's all right. This one's not bad, because what they're referring to is how the rugby player's moving. So they're referring to motion. And we hear it a lot in sports, even with cricket. They'll say that the batsman used the momentum of the ball from the bowler, okay? Or in soccer, they don't use it very often, but in soccer, we get it so when there's a cross kick across the goal and one of the players headers the ball into the goal, he's using the momentum of the ball. So he's using the motion. So when we hear the word momentum, we conjure up the thought of movement. And that's what momentum's about. It's about the movement of objects, okay? So, this is what we're going to look at through this section, okay? We're going to look at the definition of momentum. We're going to look at the equation, because it's calculations. We're going to look at the properties. We're going to do Newton's laws in terms of momentum. We're going to look at how we change momentum, what the consequences of that are. We're going to look at conservation of momentum. There's lots of conservation laws that we're going to look at. Conservation of kinetic energy. And then we're going to look at impulse. Impulse has a lot of everyday applications to it. It's actually a really important section. Then we're going to look for today. Here are our keywords. First one is momentum. Okay, what is momentum? What does it do? What is it? How do we work with it? Then we're going to look at the term vector again, and I can hear the groans. Momentum is a vector, so it's a very important thing to look at, okay? Then we're going to look at vector diagrams with momentum. I can hear the groans again, okay? Vector diagrams are incredibly useful for us. So please don't go, well, I'm not in grade 11 anymore. Vectors aren't important. Vectors are very important, okay, because they help us understand how the motion works, okay? So let's look at the definition of momentum. Momentum has to do with the mass of an object and its velocity. Remember I said when we started this with rugby players that they talk about using the momentum, so they're talking about the motion. So in other words, an object has to be moving for it to have momentum. Movement means it needs a velocity, okay? So when we look at it, mass, oh, I need to be able to write on the board. Okay, there we go. So there we go. Mass. Oh, I was just going to write mass again. That's M. V is velocity. What we need to see here is that when we define momentum, it's the product. Multiplication means product. So we're going to use that word. So when we define it, we've got to be careful that we don't say momentum is the mass and velocity of an object. That doesn't make any sense. What are we doing with the mass and the velocity? Are we multiplying it? Are we adding it? Are we dividing it? So it's multiplication, okay? It is the product of those two together. Now let's look at the equation. The equation comes from the definition. All of our equations have something to do with the definition or law that we're looking at. So if you know the equation, often it means that you can get to the definition or the law. So our equation is this. Momentum is mass times velocity. Nu, that's momentum. Okay. Please guys, it is a lowercase p. Capital P means power. Totally different concept. Okay, so this is a lowercase p. You know m is mass and you know v is velocity. That gets us to the units, all right? And momentum is a little different to what you're used to because a lot of times everything has its own set unit. But what we do with the units with momentum is it comes from mass. Kilograms is mass. Meters per second from the velocity. So it's got a unit that's made up of the units of the things we use to multiply it by. Okay? Please, you must use the right units here. Okay? And it's nice and simple. So the equation's easy. Now we need to look at the properties. Okay? We're doing a lot of groundwork today. Properties, number one, it's a vector. What does that mean? So we have to remember that when we define a vector, it means that it has magnitude. Magnitude means size, and it has direction. So we have to be able to give the momentum a direction. So forward, backwards, north, south, east, west, left, right. The direction, the way we describe the direction is going to depend on the question, okay? So we've got to look at the question and describe direction the way the question describes direction. Also, just a side note, when you look at direction and you've got a diagram, just because the object looks like it's going to the right doesn't mean it's going east. Be careful, okay? Because the way we draw the north, south, east on a piece of paper, east looks like it's going right. But that doesn't mean it's going east. It could be going north. We don't know. If they describe the object going to the right as being to the east, then it's east. Okay, so be careful with that one. It's a bit worrying because you want to give a direction in terms of compass points because that feels like a direction. But right, left, up, down, those are all directions. They all make sense. All right, so just be careful with that for me. All right. Oh, look, I've written over my stuff, but it's okay, we'll take that out. So let's take what I wrote out here. Because it's a vector, it can be represented by a vector diagram. So we have to remember what a vector diagram means, okay? A vector diagram is an arrow. It's an arrow of a specific length, where the length of the arrow gives me the size of the vector, and the arrowhead shows me the direction it's moving in, okay? So momentum's a vector, so we can give it an arrow, all right? When we get to change in momentum in a few lessons' time, this is where life's gonna get a little interesting with our vector diagrams, okay? But it's all right. We can do this. It's not that difficult. You've done vector diagrams before. All right, now, next thing. Momentum is directly proportional to mass. Remember, that sign means directly proportional. And I'll write sideways on the board. So, what does directly proportional mean? It means that if mass doubles, momentum doubles. If mass becomes 3 times smaller, momentum becomes 3 times smaller. Be careful here that you don't go, if mass increases, momentum increases. That's true, but they increase or decrease by the same factor. Okay, that's very important. Momentum depends on mass. Okay, not the other way around. Mass is the important part. Also, momentum is directly proportional to velocity. In other words, if I double the velocity, I double the momentum. If I halve the velocity, I halve the momentum. And if we go back to our rugby player situation, our big rugby players like the Locks are hard to stop because they have a lot of momentum because of their mass. Okay? Some of them can run very fast, but generally they're not as fast as like our fly half or the winger, who tend to be a little smaller. Okay? They still have a lot of momentum because they can run really fast. Okay? So even though they're smaller, they're faster. Gives them a lot of momentum. Okay? Same with a cricket ball. Cricket balls have a lot of momentum because even though they're small and they're only about 150 grams, they go very fast. If we look at our spin bowlers who can bowl a ball at like 150 kilometers per hour, heaven forbid, big momentum, okay? Very big momentum. All right, so what have we looked at in this section? The definition, the equation, and the properties. We're going to take a short break, and then when we come back, we're going to put it more into some more theory for you. Okay, so we'll take a short break.